Okay.
Okay. So what was I saying? This idea of some kind of nice two rigs, evidently it's some kind of categorification of one rigs or also especially rings. So it's not just these definitions that we're categorifying, but we're trying to categorify certain attitudes. And so one thing I have in mind is, let's talk about the decategorified case a little bit first. So imagine sort of interaction between an algebraic geometer and a commutative algebraist. So commutative algebraist, in my imagination at least, that's somebody who studies commutative rings. And an algebraic geometer applies commutative algebra in certain ways. And in particular, one of the basic ways that an algebraic geometer applies commutative algebra is that the opposite of the category of commutative rings forms the category of affine schemes. And the thing I'm imagining, again, I don't really know different cultures of mathematicians, but the way I imagine it, I imagine the attitude of the algebraic geometer to the commutative algebraist is very, very supercilious, very arrogant. I'm
working in the opposite of your category.
Well, but that makes it sound like it's just,
You've got everything backwards.
No, but it's not. It's.
I'm just joking. But it's sort of funny to imagine.
Sure. But
that's the only difference. Yeah.
But yeah, I mean,
not the only difference, I guess.
The commutative algebraist is more right. Is more on the algebra side, and the algebraic geometer is more on the geometric side. And the idea is that okay, maybe what you're saying is not so much of a joke. That things make more sense. I mean, whenever you have a duality between algebra and geometry, I mean, sometimes when you have a duality between algebra and geometry, the duality is so symmetric that you can't even really tell which side is the algebra and which one is the geometry. It's kind of a matter of convention. But when there is a contrast in flavor between the algebraic side and the geometric side, it's almost a matter of you almost define which side is the geometric side by which one is nicer. It depends on what you mean by nicer, but it's more like I think of it as more like semantic, whereas the algebra side is more like syntactic. So the geometer gets more to think like the way human beings really think.
Absolutely.
Whereas the algebraist is more thinking the way machines think, or something like that, or computers, or something like that. Accountants, or something like that.
What?
Accountants, I say. I don't know, or
Speaking of supercilious, okay, yeah.
yeah, exactly. So the idea is that, think of the, right, I mean, right, part of the problem is that algebraic geometers have this arrogance over everybody, but I'm not interested in that at the moment. I'm interested, and I'm also not interested in any arrogance that commutative algebraists have over algebraic geometers. I'm just interested in the arrogance that algebraic geometers have over commutative algebraists. And I'm asking you to sort of categorify this in your mind. So in other words, I'm suggesting that we should be,
So are you proposing we be too arrogant?
Yes. But specifically, so right, I guess right. Let me try to say it a little bit better. Let me try to put into words the algebraic geometer's arrogance. So the algebraic geometer's arrogance is this commutative algebraist. He doesn't even think about the geometric interpretation of what he's saying.
Yeah. I mean, localization is such a weird magic trick if you're just a commutative algebraist. Like, localization made no sense at all to me. How you would think to do that and why it does all these magical things for you before I learned about affine schemes.
I'll have to think about that. I'll have to think about that. But yeah, that's an interesting point. But I'll have to think about it later. But you know, so first of all, imagine the categorified commutative algebraist who just like studies two rigs. Nice categorifiedly commutative two rigs. So symmetric monoidal or something like that. And but then imagine this categorified algebraic geometer who's contemptuous of the categorified commutative algebraist because in his mind at least, their mind at least, they're thinking they're thinking this person isn't even thinking about the categorified geometric interpretation of what they're doing. They're just sort of thinking about these symmetric monoidal categories as just algebraic objects or something. So that's what I wanted to say.
But then, of course, the challenge is, okay, how do you think about the geometric meaning of these categorified entities? So that's sort of the responsibility of the categorified algebraic geometer, not just complain about someone else not doing it.
Right. And so one of the funny tricks that's going on here is that you might expect that the typical examples of the categorified commutative rings would be categorified, that their geometric interpretations would be categorified compared to the uncategorified case, but it's not. In other words, the first trick that happens is that you know you have like you have an uncategorified commutative ring. Let's call it A, and that has a geometric interpretation, which is the spectrum of that commutative ring as an affine scheme. But then we go searching for somewhat typical examples of the categorified case. So we're going to have a categorified commutative ring, or perhaps better, categorified commutative ring. We're going to have a categorified spectrum of that commutative rig, that categorified commutative rig. And we're going to think of that categorified spectrum as a geometric object. And the funny thing is that the most immediate examples are actually giving us the exact same uncategorified spectrums as we started out with. So what you do is you take, as your first example of one of these categorified commutative rings, you take the modules of a commutative ring. And so that's a symmetric monoidal category. It's got colimits and everything. And its spectrum is real. When you think about what its spectrum is, that is really just the same spectrum as the spectrum of the commutative ring. So what I'm saying is, if you have a two homomorphism from the modules of the commutative ring into the category of abelian groups,
okay,
that's basically the same thing as having a homomorphism from the commutative ring.
Right.
I hope I'm saying it right, into Z, I guess.
But this is like Eilenberg-Watts, right?
Okay, I'm not quite familiar with terminology Eilenberg-Watts. Can I just write this down? What is it?
That's a theorem. I think the Eilenberg-Watts theorem says that symmetric monoidal functors between two module categories are always tensoring with a bimodule.
Okay, but this sounds like it sounds unnecessarily general in the sense that you do that doesn't sound like it's just about commutative.
Right, but when you restrict attention, when one of your category of modules is abelian groups, which is Z modules, then I think this should be the same thing as getting, I think you should be able to get that from this precisely.
Sorry, I'm just trying to make the stroke width a little bit narrower here. Sorry, okay. Eilenberg Watts, just one thing I should look up. I mean, yeah, it does sound like it does sound like a very I mean, the idea of Eilenberg's name being attached to this does make it sound almost tautological in terms of just like time extension or something like that. But anyway, I just wanted to note that for myself. But yeah, so yes, there's probably some very commutative or stable instance of this Eilenberg-Watts thing that you're talking about. That would be what I was saying there. And I was going to try to say, I'm not sure how to say it exactly right. I mean, so what am I trying to say? I mean, so like one of the things that people sometimes do when they're thinking about like, you know, supposing the idea of categorifying a polynomial, categorifying the idea of a polynomial. Well, there are at least two ideas about how to interpret that. And one way is to take, you know, a symmetric monodal category that's sort of like free on one object or something like that.
Yeah.
And that's certainly an important thing to do. But it's very different from this other thing that I'm talking about, which is to take the category of modules of the uncategorified polynomials.
Right, yeah.
And then take that as a theory. And so the spectrums of those two things are very different. And you know, by the Eilenberg-Watts idea, the spectrum of the module category of the uncategorified that's really just the spectrum of the original polynomial ring.
Right.
So really just the affine line. Whereas even to give meaning to the spectrum of the categorified polynomials, I mean, that's a very interesting thing to think about, but it's going to give you different things.
Yeah.
Sorry, was that supposed to be the free 2-rig of this type on one?
Yeah, so like Joyal species or something like that.
Right.
Yeah, or maybe a linear species.
A linear version, yeah.
Yeah, or something like that. Yeah.
Todd and Joe and I are always working.
Yeah. Well, I mean, again, it depends on what. I mean, you know, when we talk about polynomials, I'm always being vague about what ring the coefficients of the polynomials are coming from. And so we just categorify that vagueness that, you know, when I talk about categorified polynomials, I'm probably being vague about what, you know, unless I need to be precise, you know, I'm probably talking about all possible coefficient domains at the same time. I mean, so that shift between those two examples is, I'm tempted to express it in some sort of language, like in one case you're looking at sort of like pi 0, and in another case you're looking like pi 1. But I'm not sure what I mean by that. I'll have to think about what I mean by that. But there's some dimension shift, categorification dimension shift or something like that that's coming into play here.
So is there a theorem, or are there dreams of a theorem that most let's say commutative 2-rigs come from module categories of something or some flavor category?
That's not exactly what you want. I mean, it's you know, it's a good question. It's very related, but so like, what am I trying to say? So supposing you have a quasi-projective variety. So it could be like either quasi-projective variety includes both the affine varieties and the projective varieties. Or maybe you can say the same thing with schemes. I'm not sure how the terminology works, but maybe there are quasi-projective schemes, which would include both the affine schemes and the projective schemes. And so roughly speaking, there might be some technical details I might have to worry about, but roughly speaking, you can take a quasi-projective scheme and talk about the quasicoherent sheaves over it. Now that quasi is those two quasis, I think, are
yeah,
but
they're also quasi-compact, which I think is yet another not quasi.
I don't know. I don't know about that one. I'm not going to worry about that one at the moment. But so in the case where the quasi-projective scheme is in fact an affine scheme, then the quasicoherent sheaves specialize to the module.
Right.
Yeah. But in the case where it's a projective variety, they don't. It's an independent concept. And so
yeah, is this something, one thing John was telling me while there were still technical issues happening sooner, is that one of the reasons to do this categorification is it takes things that used to be projective and makes them look too affine.
That's right. That's right. That's what I'm trying to say. So rather than trying to get, you know, rather than trying to get the two affine things to be like the affine things,
right?
We're treating it as very much of a feature, that it gives you more, and that it gives you things like the like the projective varieties or the projective schemes rather than just the affine ones.
Yeah.
So let me try to give you a very rough example here. Okay. So like, and again, this will be sort of from the point of view of categorified generators and relations, or, you know, some like a sketch or something. But categorified generations and relators in some sort of doctrine of something like symmetric monoidal locally presentable categories.
Sure.
Or roughly speaking, symmetric monoidal co-complete categories, but you have to be a little careful what you mean by co-complete. So let's yeah. So in this doctrine of the nice two rigs, let's take the free thing on there's technical details here, but I'll try not to worry about the technical details too much. I want to say something like, well, if I say, supposing I take the free thing on an invertible object, or invertible meaning invertible under tensor product.
Ah, right. So something like a line bundle.
That's right. But if you just start with that, well, so first of all, if you just say invertible bundle, if you just say invertible object, it's probably going to end up being more like a super line bundle than like a line bundle. So maybe, but maybe I want to avoid that. So maybe
I'm not sure what you mean by that, and maybe I won't ask, but
yeah, well, in fact, so there's a slight improvement on the concept of an invertible object, which is a line object. And basically it's just saying that the way the the invertible object tensors with itself, and the way the braiding works on the invertible object tensored with itself is more bosonic than fermionic, or something like that. There's no sign twist or something like that.
Got it.
So it's an invertible object where the braiding from it in itself is the identity morphism. That's
Yeah, something like that. I always get confused about how to say that, but yes, that sounds right. Whatever, John.
Yeah, I know embarrassingly little physics, which
Okay.
I will try to rectify at some point in my next 70
well,
years.
you know, yeah. Well, anyway,
Okay, so actually we can just stop at that point. We can just, in giving us our presentation or our sketch, we've now finished the presentation or the sketch, and we just said the free thing on a line object.
Mm-hmm.
And so we can ask, is that some familiar 2-rig?
Yeah.
And it is. And is there any guess you want to take as to what 2-rig that is?
Free 2-rig on a line object.
And again, there might be technical details. There might be technical details here, depending on all sorts of annoying things that I don't want to worry about. So I'll pretend that we don't have to worry about so many of the technical details here. So
I want to say that I want some guy where halming into it is the same thing as giving me line bundles in my space. And I should know what that is. That's like, oh, that's what, CP1 or something, right?
it's related in some funny ways.
It's
It's interesting that what you said there.
What?
It's interesting what you did there, Chris, because at first I thought you were aiming for. So there's a topological space such that with a line bundle on it, such that to pick out a line bundle over any space.
No, I wasn't looking for a classifying thing.
Okay.
Yeah, I would
sound like you meant that. That would be BU1, or which is CP infinity, if we're working over the complex numbers.
I believe you. Yeah.
But it is related to this other thing that you then said, which was CP1.
Yeah.
So what were you thinking that made you say CP1 anyway?
I was thinking, is there a scheme?
There's definitely some funny level subs here, but go ahead.
Yeah. Maybe I was thinking about like BU infinity or whatever.
Yeah.
Yeah, because, but yeah, I was thinking about, well, okay, on the algebraic side of the story, we have the free thing on a line object. So halms from this guy into my favorite 2-rig should be line objects in my 2-rig.
Yeah.
Of course, we want to think about this geometrically. So we actually want to say that halms from my 2-rig to this thing geometrically should be line bundles on my 2-rig. And then I started thinking about what is a geometric space where halms into this geometric space are the same thing as line bundles on here. And you're right, I think that I was probably thinking about some sort of classifying bundle. But I don't know what prompted me to say CP1. I think somewhere.
Right. I was halfway expecting you to say CP infinity.
Yeah.
But then there's interesting stories about how CP1 comes into it as well.
It could very easily have been somewhere halfway between misspeaking and misremembering, but.
Well, so unless you want to take further guesses, let me just tell you what I think the answer is. Yeah. So it's so there's a couple of ways to express it. One way to say it is that it's the category of representations of GL1.
Okay.
So now John was saying something about U1, and I think he meant
that was
the group U1, but that's probably some difference in doctrines between John and me or something like that, or John, John is leaning over towards a slightly different doctrine or something. Yeah.
I should have said BGL1. Yeah, that's what I.
Yeah.
Purposes of the present conversation. Topologists.
But also you have to interpret about what you mean by BGL1, because this is more like an algebraic or algebraic or categorified algebraic version of BGL1. I mean, it's a stack. It's classifying stack more than a classifying space. But, you know, concretely, it's basically just the representations. Well, I mean, and right, yeah, and you have to look at the fine print of what representations means in this context. So we're, you know, it has to do with the idea that we're treating GL1 as an affine algebraic group.
Right.
And that actually means that it's a commutative Hopf algebra.
Right, and so you want to look at the co-modules, which has
Well,
been
you want to look at the co-modules, that's right.
a disappointing problem, and another problem that I'm thinking really hard about right now. It's working with co-modules instead is making my life really hard.
Oh, it's actually the co-modules is much nicer to work with. And there's, I mean, there's good reasons why it's the co-modules. But so these co-modules, in this particular case of GL1, the co-modules of GL1, if you think about what that is in a sort of concrete syntactic way, it's really just Z-graded vector spaces. Or, you know, maybe you could say Z-graded abelian groups if we're really working over a base of abelian groups or something like that. And you can see this very syntactically in terms of the generators and relations. So there's, you know, we you know, there's supposed to be that generating object there, that generating line object there, and we can see very concretely what it is. So it is just the unit vector space or the unit abelian group or whatever, concentrated in grade 1. Or it's hard to tell the difference between grade 1 and grade -1. It's a matter of convention. I'm not sure which convention I should be using or something like that. But that is, you know, that is, so what is that? Is there a name for that representation of GL1, John? Is that like the tautological representation?
You would call it the tautological representation. So GL1 is 1x1 matrices, and it has a representation on vectors of length 1, and that's the representation. Yeah. So tautological representation, that's fine name. Yeah.
Yeah. Okay. So with
So there's that representation, by the way, and then there are all of the tensor powers of that representation. And because it's
including the
direct sums of those, and then there's the inverse of that representation, the tensor inverse of that representation, which is the dual. And that's where this line object thing comes in. The fact that this is a line object means that the dual actually acts as the tensor inverse.
Sure, yeah.
Well, I mean, when you have an inverse of an object, it acts as a dual. That's the right way to say what I said. That is, you have an isomorphism between the object, tensor its inverse, and the unit object.
Yeah.
And that's even
an inverse is a very strong kind of dual. Yeah.
Yeah, it's better than them being just dual to each other, where you'd have a unit and a co-unit going back and forth. So you get, that's how you get Z. You get all the powers of this line object. And then you can start taking direct sums of them, of such things. And so then you get Z-graded vector spaces. You just sort of say how many, the vector space for each integer tells you how many copies of.
Yeah.
And this really is a good example of how nice co-module categories can be of commutative Hopf algebras.
Yeah.
They're very syntactically nice in this way. I mean, there's a lot of other interesting examples to look at. But so I mean, right, so this was a very sketchy sketch. I mean, it's like, you know, we said we might have like generators and relations, but really mostly we just had a generator. I mean, it's, I guess, a line object rather than just an arbitrary object, but still it's mostly just.
You were going to ask about the spatial way of thinking about it. I thought that was your question, Jim. That Chris was attempting?
Yes, that's right. So, right, if you're thinking about the universal property of this,
like what space
is space
we're talking about here?
It's very stacky. It's right. I mean,
Yeah.
It's supposed to pick out line objects, but line objects have automorphisms.
Yeah.
And endomorphisms, I guess, whatever. But so we're dealing with a space, if you think of it as a space, but whose points have automorphisms. So it's a very stacky space. So in other words, I mean, one of the things you can see is that from our first example of the commutative modules, that was giving us very unstacky spaces. And from our second example of group representation categories or comodules of commutative Hopf algebras, that's giving us purely stacky things. Just like, there's just one point.
Right. Yeah.
Yeah. And so.
Right. BGL1 was what we said it should be.
Yeah. And so the whole subject is sort of a blending of these two flavors of examples, the very unstacky things and the purely stacky things. And I mean, how does it work? It's like, right, I think it's basically sort of like, the object generators are giving you the stacky stuff, and the morphism generators are giving you the unstacky stuff.
Oh, interesting.
Yeah. And so when you start blending together the object generators and the morphism generators, that's when you start getting things that are neither purely unstacky nor purely stacky, and you're getting these blended things that are, interestingly stacky in some way. But so let me just give some examples here. So like we could have like the free nice 2-rig on a line object, let me call it L, on a line object L equipped with again, I'm going to use some sloppy language here, but this example does make sense when you clarify all the definitions and stuff. But the free line object, the free nice 2-rig on a line object L equipped with, I'll say equipped with an embedding into, let me say, for example, the second, the direct sum of 2 copies of the unit object. If you want, you can do direct sum of 3 copies of the unit object or whatever like that. Equipped with an embedding. Now, what does an embedding mean in the, you have to define what we mean, but it turns out it means more than just like a you can't even say monomorphism in this doctrine, because it involves limits rather than co-limits. Right. But there are tricks you can use to, especially these tricks have to do with the fact that, we're dealing with invertible objects, and these invertible objects have this very strong duality, so you can turn things around. You can talk about epimorphisms instead of.
Right, so you could ask for like a reg epi between the inverses or something.
Something like that, but again, you have to figure out what regular means in this context.
Well, by reg epi, I just mean a co-equalizer.
But even that, let me think. Okay, that's saying this technical fine print you have to worry about. Just because of the fact that saying that it's a co-equalizer, that's sort of existential. There's an existential quantifier there. There's not an obvious.
Oh, you want it to be operational.
For it to be, yeah. So.
Yeah, sure.
There's slight subtleties here, but you can get it to work. So.
Wait, sorry. In nice categories, where I guess by nice I probably mean regular, I think.
Yep.
Maybe you can get by with less, right? Every co-equalizer is a co-equalizer of its kernel pair. So at least there's a unique choice you can.
Yeah, but again, the kernel pair is going outside.
Oh, but that's limity again. You're right. Yeah.
But there are things, I mean, there's all sorts of different things you can try here to fix these problems.
Yeah.
But the way I usually like to fix it involves not using the concept of regular epi, but I just have some substitute for the concept of a regular epi.
Sure.
That parses in a good enough context. So you have any guesses about what this example would give? Concretely, what is the, from a sort of syntactic viewpoint, what is this presented symmetric monodal category look like? And again, it's hard to guess because I didn't give a very precise definition of.
Yeah.
So I sometimes call these, I sometimes call them good embeddings or something, and they're sort of like the dual of a regular epi or something like that. But yeah, were you gonna say something, John?
I was just coughing, but I will say something.
Coughing, yeah.
So you said like equipped with some kind of nice embedding from L into 1 plus 1. Is that what you were?
Yes. From L, that's an example. From L into 1 plus 1.
Or 1 is the unit object in our.
Yeah, with the unit vector space.
Yeah. So if I'll just say that in a more bundly language. So we're trying to dream up a space, but it could turn out to be a stack or something. Which has a line bundle on it. That's our L. But now, which we did that one. But now our line bundle is embedded into the direct sum of 2 copies of the trivial line bundle. So you think of 1 as the trivial line bundle. So we've got like a 2-dimensional trivial bundle. And then we've got a line bundle and it's embedded in there somehow. So like you can imagine such, like just if you're doing like the real numbers and like the Mobius strip bundle on the circle is embedded into 2 copies of the trivial bundle. That's which is the normal bundle of the circle. So that's like an example. That's not the free one there, but that at least is an example of a space with a line bundle on it that's embedded into the direct sum of 2 copies of the trivial bundle. Well, and you could imagine that for the complex case or whatever. I guess Jim's sort of not even saying what field we're. So, but then you have to somehow think about the free one. So I don't know if what I said helps at all. Think of figuring out the free. It actually does, actually.
No, I think it does, is the thing.
Yeah, right. And so again, there's at least 2 flavors of answers we could look for. More syntactic or more semantic, more algebraic or more geometric. Saying what these objects are in the symmetric monodal category, or saying geometrically what the spectrum, the categorified spectrum of this 2-rig is like.
So just the line bundle we decided was BGL1, but now our line bundle is equipped, like John said, with some embedding into a trivial, not line bundle, but
Yes, into the standard trivial line bundle of dimension
2, yeah.
Dimension 2.
Another small observation is we've now essentially added a generator. So on the syntactic side of things, right, we've added this bonus information of an embedding into 1 plus 1. So that should give us, because that's adding an arrow. So our
Yes, a morphism generator, not another object.
exactly, it's a morphism generator.
Yeah.
So that tells us that in some sense, our syntactic category on the syntactic side should be bigger. Which
Bigger meaning that there's what, a map from,
It's hard to tell whether it's bigger or co-bigger because there's so many adjoint things going on.
but there is a map.
Kind of a funny turn of phrase. I actually like. I've never heard co-bigger before. But yeah, huh? Do I mean co? Okay. Well, anyways, but you could turn that into trying to figure out whether there should be some inclusion of BGL1 into something, or perhaps a quotient. I would need to think hard.
There definitely should be a map going one way or the other. So there's a map of two rigs from free two rig on a line object to the free two rig on a line object
with junk. Yep. Which tells us that geometrically, right, an inclusion over here should be an epi over here.
You're being very optimistic about the epi and inclusion stuff, but
No,
I'm happy just to have a map for starters. Yeah, so there would definitely at least be a map.
Yeah, but if all is right with the world,
yeah,
inclusions on the semantic side should be, or syntactic side should be some sort of quotient on the semantic side. So I guess we want something that quotients to BGL1 in some way, but I don't see a natural cover.
That might be true. That might be true. I mean, it sounds like you're saying, you know, the original classifying stack possesses the universal bundle, and now this is a slightly less universal bundle or something like
right
that.
Yeah, yeah, I guess that is what I'm saying. And so the slightly less universal bundle should in particular be a pullback of the actual universal bundle. But
I guess that's right. I guess, yeah.
But again,
and that pullback, that pullback is really just, you know, from the dual algebraic point of view. That's a push out.
Exactly.
Push out is this generators and relations.
Exactly. Yeah. And again, we're all lying to ourselves here, right? We're closing our eyes and claiming we're doing geometry, but really we're all doing algebra at the end of the day is the way you prove things. And this all becomes
you
just make the definitions to make the geometry the thing you can compute. But, yeah. Do you have an answer for what this should be? Have you?
So again, there's some fine print that needs to be. Well, there's some fine print that needs to be cleaned up, and actually, other people help me with this fine print. But roughly speaking, we're saying this is. I guess this is your guess for the other one. This is CP1 or something.
Oh.
Yeah. Because right, we're saying, right, we're sort of saying, you know, again, try to think geometrically, try to think very directly. So we're saying a point of this space or categorified space is a line object equipped with an embedding into this standard two-dimensional vector space. So it's like a one-dimensional subspace of this standard two-dimensional subspace. So that's like the projective line. And that's, you know, in that one example, that is the general philosophy of how this whole story works.
Yeah.
And so there's, you know, all sorts of variations you can do in this. Like, let me just.
That's
how much?
Really, like,
yeah, go ahead.
How much of this stuff? You'll have to forgive me for asking this type of questions, but how much of this stuff, Jim, has really been written up precisely?
Well, a lot of it had been written up by, I can name some of the people who wrote it up, but go ahead, yeah?
Yeah, so, well, this particular thing,
I'm pretty sure it's in Martin Brandenburg's thesis.
Yeah, that's actually on my to-read list. That's pretty fun.
Yeah, I think it's a good thing to read. And there might be further references in there.
Because to do it right, to do it really, really right, you'd want to sort of have worked out some theory of these sketches.
Yes.
No,
There are
Yeah.
different levels of doing it, depending on how much of the sort of talk that we were talking one wants to actually convert into the being like an example of the thing you're allowed to say in some rigorous framework.
Yeah. So can I mention here that one of the things that's going on here is that, again, we're sort of interested in this relationships between affine varieties versus projective varieties, and how those both fit in as two affine varieties. And what am I trying to say? That, see, if you look at the sketches that we gave for like the affine line, which is basically just, free on one quantity, one morphism from the unit object to itself or something like that.
sure, yeah.
That is purely just morphism generators. So that's why it turns out to be an affine variety. But when you sketch the quasicoherent sheaves over the projective line, you don't get by with just morphism generators. You really need object generators as well. And this has to do with why on the projective line there's a shortage of globally defined functions. There's a shortage of holomorphic functions. That's sort of the whole idea why this needs to be a projective variety instead of an affine variety. And so what am I trying to say? That the real conceptual hallmark of projective varieties is that they don't seem stacky, but they have a sort of hidden stacky aspect to them, because in the presentation, in the sketch, you need object generators, not just morphism generators. And this has to do with the idea that a point of a projective variety is actually more than just like a number. It's actually an object. It's a subspace. And then you have the same kind of thing with all sorts of other varieties, which maybe you can think of as projective varieties, but there may be independent ways of thinking of the points as being objects of some kind. So like when you have a Grassmannian or something like that.
Yeah.
So you can, if you want to sketch the theory of a Grassmannian, you're probably going to put in, an object of the dimension that the Grassmannian, and then it's going to have an embedding into some other fixed object or something like that. And so you can sketch Grassmannians in this very similar way.
I think you should actually be able to get all toric varieties. I think there's a paper that I read about 100 years ago, but I could find for you, that gives a description of
I thought about this a lot, but go ahead. Yes, go ahead.
Oh, that gives a description of what toric varieties represent, right? So like Grassmannians represent certain K subspaces of Cn, say.
Yes.
But you can think about every scheme represents some functor, and you can ask for a more algebraic description of what that functor is. And I think somebody has worked this out for all toric varieties. And I didn't read the paper super carefully, so I can't tell you what that representation is, but I know it's been done.
There's a lot to say about toric varieties in this context. I mean, one of the things that happens is that with toric varieties is it's actually very interesting to think of the categorified coefficient as being sets instead of being vector spaces or abelian groups.
Yeah,
and that has to do with the idea that the analog of a commutative ring in toric geometry is really a commutative monoid.
Right. Exactly.
Yeah. So it turns out that it's very interesting to look at the there's like a toric version of quasicoherent sheaves. Anyway,
Sure. Okay.
this is a little bit of a digression, but there is definitely interesting stuff to say about toric varieties here. But another example I was going to give is something like, I mean, supposing you put in a generator, and let's say it's an object generator, and you can also give it like a Lie algebra structure. And then you could just stop there, and in some sense that would give you the modular stack of all the algebras.
Chris is looking unhappy. So.
I mean, you
Yeah.
can do this,
What do you
right?
want?
You can just put in an object, and then you can start putting in, you know, morphisms between its tensor powers that would make it into a Lie object.
But confirming the equations is a limity thing to do, right?
Say that again?
Confirming the equation, so you know you want the Jacobi identity to hold.
Yes, yes.
Probably important, but that amounts to taking equalizers, right? A Lie algebra is a finite product theory.
No, it could work out if we do it right. Let me think. What am I trying to say? So first of all, let's note that
Unless you do the trick from before where you dualize everything and actually put
yeah, but maybe what's saving us is just some simple level slip or something like that. I mean, right? We're doing categorified presentations, so we now have not just, you know, generators and relations, but we have three levels. We have object generators, morphism generators, and equation generators. So those equation generators are just I mean, it works out. You can work it works if you do it with co-equalizers instead of equalizers. There's a way to get this to work.
Okay.
But I mean, also if you just don't even specifically think in terms of equalizers or co-equalizers, just think in terms of you're just setting
right, you're setting
morphisms equal or something
right.
like that.
Yeah.
I mean, you could
You can have, like in a Levere theory, you can have like equations between operations.
But I mean, there's also interesting stuff here. I mean, there's a way you can think of it as inverting a comparison morphism between a co-equalizer and another and in that way you can in that way it does involve co-equalizers in a way, but it doesn't involve equalizers. I mean, if you were working in a doctrine that had equalizers, then you could do it that other way by inverting a comparison morphism between an equalizer.
Right. But also you could just say, right, because you're totally right, we're presenting a category. So you're allowed to have object generators, morphism generators, and you're allowed to, you know, impose relations on such things.
Yes,
so you're allowed to say that certain squares commute, and you can say the diagram morphism squares commute. Okay. That's
right. So it just kind of works naively, but there's also interesting ways to think of it related to co-equalizers and stuff like that. So in this way, you get something like the moduli stack of Lie algebras. Roughly speaking, the way we just said, although you very well might want to say, in order to prevent some unpleasant things from happening, you might want to put into your definition of a Lie object that it actually has a dual, that it has an adjoint.
Sure.
I mean, that will certainly make things nicer, but better behaved in a way. But you also might, you know, and once you have these adjoints, there are ways that you can talk about the dimensionality of an object. So you can say, you know, the moduli stack of all three-dimensional Lie algebras or something like that. And this all fits into this syntax of these nice two rings. So that's sort of the philosophy of it. And this should also
go ahead. John, was there something you were going to say like 30 seconds to a minute ago?
Well, one thing I was going to say is that Jim started saying adjoint when a second ago he had said dual. So I just wanted to
Yeah.
I'm not sure which I prefer to
Well,
say.
The
although
same thing.
I was gonna say one of the worst definitions that I've ever read, that is my current pet favorite terrible definition, is that the dual of a vector space is a left adjoint in the d-looped by category or whatever.
Uh-huh.
Uh-huh.
I think I like that definition.
Well, okay.
Well,
they-
I might have to
afraid
check, I
you're
might have to check the
falling
fine
in with the
print.
wrong crowd, Chris. I thought that's what it was.
No, I think it's a good definition,
Yeah,
and
no,
it actually did explain what's
a
going
good-
on with the
no, it's not the good first definition you should ever hear, usually, unless you're.
Yeah. It's a terrible
unusual
first definition
education.
and a great ninth definition.
It's a terrible
So-
first definition for, depending on which direction you're coming from.
Yeah.
There actually are strange directions you could.
Yeah.
If you somehow found a way to learn about higher categories without learning about the dual of a vector space,
I think I did. I'm not sure. I'll have to think about it. I'll try to remember that. But
So anyway, well, I was also going to say that it's not supposed to be completely obvious how using the assumption that our object has a dual, that you can define a dimension of it. But there are actually a couple of ways.
there's some unfinished collaborative work here between John and me, but go ahead.
Yeah.
And stealing from a whole bunch of other people. Go ahead. Yeah.
Yeah. So I mean, there are sort of at least two interesting things you can define. So one is, if you have an object with a dual, you can talk about the trace of a morphism from that object to itself, because you can take that morphism and stick a cap and a cup on it to get a trace of it. And so one way to define the dimension of an object is that it's the trace of the identity morphism.
Yeah. Which
so one interesting thing about that is that it's not even obvious why that should be an integer.
Well, it's not in general, right? It's the
Right,
it's
not in
it
general.
lives in like end of I or something, or end of one.
Right.
Yeah,
That's
yeah,
true.
Yeah.
Yeah.
Just so to say, when I said it's an integer, I mean it's like an integer multiple of the identity in
Sure,
end of
sure.
one.
Yeah,
But
okay.
you're right. But
No, I was being too pedantic. I could have figured out what you meant.
well,
yeah.
but anyway, there's no reason why. There's no instant reason why it has to be an integer multiple of the identity in end of one. So there's some questions there.
Is
Like
it in general?
what kind of dimensions things can have? Sorry?
Is it an integer multiple?
So
That's super
What is
I mean, a very
mean in this
famous
context?
thing is
Go ahead.
very famous thing in some circles is that if you work in braided monoidal categories,
okay.
you get these non-integer dimensions of things. So you're messing around with representations of quantum groups that are braided monoidal categories. You can have representations that have what they call non-integer dimension. But for symmetric monoidal categories, you're closer to being able to show that things need to have integer dimension. And so there's a theorem called the Doppler-Roberts theorem that gives some extra conditions under which you'll definitely get integer dimension. But even there, it can be a negative dimension. And so we were going to stay away from supersymmetry, but these fermionic objects that we were alluding to, only to say that we weren't going to talk about them, they can have negative dimensions.
Is that Roberts the higher geometer Roberts, or is that a different Roberts?
No, it's an older Roberts. A John Roberts, old guy. Yeah.
Okay, but I'm a little confused. Is she still a category theorist of some kind?
Yeah, I guess Roberts was some kind of category theorist. Yeah. And Doppler was a quantum field theorist. They teamed up to try to find assumptions on a symmetric monoidal linear C linear category that would make it category of representations of a group. of finite dimensional representations of a group. And so part of the trick was to like figure out what assumptions you needed to be able to talk about the dimension of an object in there. Because if it's going to be a category of finite dimensional representations of a group, then they do have a dimension, those representations. So part of they had an elaborate program, but part of the program was like figuring out how much you needed to assume so that at least your objects would have dimensions to them.
Right.
So it's interesting, and I wish I understood it better than I did, because I have a feeling that it should all be very nice in the end, but it's sort of hard to find a really nice explanation of it.
Yeah, now it's also very likely that that this Doppler-Roberts, that's the name, Doppler-Roberts?
Yep. Uh-huh.
That this circle of ideas, it's very likely that it has its most natural expression in some doctrine or something like a doctrine that's slightly different from the doctrine that we've mostly been talking about so far. But it's definitely related, and it's interesting to try to adapt the Doppler-Roberts ideas over to the doctrine that we've been working with. And again, that's part of some things that John and I have been talking about at various points.
Yeah, they were assuming a bunch of other bells and whistles on your category, which make it be in some other doctrine or something.
Yeah.
But it sounds like it's some sort of like Tanaka type theorem.
Yeah, it's like
a lot of what we're talking about is very Tanakian in philosophy. Yes, what were you gonna say, John?
Yeah, so the big difference is that in the Tanaka reconstruction theorem, you assume you have a category equipped with a functor to vect.
Right. Yeah.
And so they were not starting out with a functor to vect. They were just starting out with some symmetric monoidal vect-enriched category. And so part of their job, one way to think about what they were trying to do is they were trying to figure out how you could cook up a functor to vect out of thin air, so to speak.
And then take end of it.
Yeah, and then use it. So that it is connected, but it is sort of like it's harder to do. Also, what's the guy's name? Sorry, I'm forgetting the famous. Dolan wrote a big paper about this type of stuff in the 2000s, trying to
About the
sort it out.
integer.
Well, he wrote some funny stuff about non-integer dimensions, but I was talking about a sort of something that's sort of more like the Doppler-Roberts theorem, but more in the kind of doctrine that we're talking about.
Okay, then that's okay. Then I'm not sure. Do you have anything close to a reference on that? I mean, just Dolan.
I could quickly get it.
All right, that might be a useful thing for me to look at.
Yeah, so maybe I'll share my screen just so you can see what I'm staring at. So there's an NLab article. So okay, it's 1990. He wrote this thing, categories, Tanakian. And so apparently there was a mistake in some earlier work about this subject. And kind of, oh yeah, and then there's a follow-up. Yeah, this is actually maybe the one I really, category tensorial by Dolan. And so if you want something that's in English, then there's a kind of summary of it on the NLab at this link. Dolan's theorem on tensor categories. And this link here, which I'm attempting to click, was written, this article here was mainly written by Urs Schreiber, who got really interested in this at some point. And so it goes it's quite expository for in lab articles. And so it's about linear tensor categories and characteristic 0. And then there's some subtle constraint that has to be added. But then when that's true, these categories are categories of representations of supergroups. So that this super stuff that I keep alluding to, Chris, about like bosons and fermions sneaks in here quite naturally. And then if you don't like it, you can put in some extra condition that says it's just makes it be a category of representations of a plain old group.
And what I'm currently doing, maybe tell me if this is totally naive. Every time I hear someone say a super blah, I replace it in my head with a Zmod 2 graded blah. And that's about where my knowledge of super things begins and ends.
So that's a good
first
most
people think of it, but I'm not sure that's the best way to think of
it.
It probably isn't the best way to think of it. It's but unfortunately the word boson is like totally terrifying to me. Like I couldn't even I couldn't even start to tell you what a boson or a fermion. Like I don't even have like a high school physics knowledge of what those two
are.
What, your high school didn't teach you about bosons?
I mean, there's a very confusing history of it.
Anyway, we may be digressing a bit.
Well, yeah, I wanted to add a few things in here.
Yep.
So right. I guess one of the ways that I mean we've just sort of seen people talking about Tanakian stuff, Tanakian categories or something like that. And I often tend to use that terminology myself, but I have a feeling that I tend to use it to mean something slightly different, maybe arguably very different from the way some other people use it. So, I mean, the theme one of the themes that we're seeing here about Tanakian categories and Tanakian reconstruction from Tanakian categories or something like that is that very often one of the things that people try to reconstruct from a Tanakian category is something like an affine algebraic group, or possibly an affine algebraic supergroup. And and when I talk about the Tanakian philosophy, I tend to mean something a little bit more general than that, which is, I mean, one way to roughly summarize it, this isn't a lot of fine print here, but one way to roughly summarize it is that I'm interested in a more general notion of Tanakian category, which is not like the co-modules of an affine algebraic supergroup, but rather is like the...
He switched into saying co-modules because he was starting to think of them as those groups as Hopf algebras. So just to
but right. I mean, but then I was hesitating whether to say commutative Hopf algebras or super commutative Hopf algebras, but it's something like that. So in the geometric language, this more general thing that I'm interested in is, I mean, instead of saying co-modules, maybe I just said representations. But if I switch to the algebraic language, then I will say co-modules. But so representations of these affine algebraic supergroups, but the more general thing I'm interested in is the representations of these affine algebraic supergroupoids. Or in the algebraic language, that would be co-modules of supercommutative or maybe I don't have to say super, if I just think of super
Yeah.
commutative as a special case of commutative in some funny way, is comodule categories of commutative Hopf algebroids. That's what they're called. So
Now, would
Yeah.
would you say super Hopf algebroid or is it Hopf super algebroid?
say that again?
Is it super Hopf algebroid or is it Hopf super algebroid? This question doesn't
I'm
matter.
not quite,
I
yeah,
just
I'm not
wanted
quite
to say
sure.
any
I might
words
have
that-
to stop and think about it. It probably doesn't matter, but I'm not sure.
No, I'm very confident it doesn't matter.
Well, I'm not sure it does. But let's see. But see that I mean, but I'm just trying to give this idea of what my idea is of the way I tend to use the word Tanakian as descriptive of a philosophy. So I'm not just applying it to groups, I'm applying it to groupoids. And that means that I'm not just applying it to these purely stacky stacks, but I'm applying it to all sorts of other stacks, which can be purely anti-stacky as well, or they can be a blend of the stacky and the anti-stacky.
Sorry, really quickly, what do you mean anti-stacky?
Those are the ones that are just affine varieties.
Oh, I understand.
So lots of objects and not many morphisms.
Yeah,
If you think of a world of groupoids, they're like at the one extreme, in the plain old unfancy case, at one extreme, they're the sets that have lots of objects and only identity morphisms. And the other extreme, there are the groups, which have one object and lots of morphisms.
So let me try to say one more thing.
One of them sort of flat, and the other is like a dot with a lot of
junk going on. Yeah, that makes sense.
I just want to try to say one more thing before we really should quit here. So I'm sketching this philosophy of studying these categorified geometric objects by means of, a sort of dual categorified algebraic object. These these categorified rigs, or these two rigs, these nice two rigs. And so I'm working in this doctrine of these nice two rigs. And the theories in this doctrine, they have this geometric spectrum, and it's things like the moduli stack of all these different kinds of moduli stacks I was mentioning, like Grassmannians, projective varieties, affine varieties, moduli stacks of Lie algebras, et cetera, et cetera. All sorts of things that you can invent and play around with. But what I'm trying to emphasize here at the end is that it's very interesting to compare working in this doctrine to working in certain other doctrines. In particular, working in the doctrine of ringed toposes, ringed toposes, or ringed geometric theories, or geometric extensions of the theory of perhaps local rings or something like that. And because the same kinds of theories can be expressed in that doctrine too. So you can talk about the classifying topos for Lie algebras, or the classifying topos. You can make projective space. There's a classifying topos for that. That the points of this topos. I mean, there's lots of fine print here. I'm trying to avoid, but so it's very interesting to try to connect the work in these different doctrines by means of interpretations of doctrines. And that's just sort of the comment that I wanted to make. And then I just have one more comment, which is that I really do want to talk about the stuff that I had planned for today, which was completely different. So maybe next time.
Well, we can do that next time.
Yeah. What? I also, before, I wasn't sure if we were about to move on, but it feels like we may be about to leave, so I should definitely say what I was going to say. Talking about, I actually wrote this down because I wanted to make sure I didn't forget the question.
Yes.
so you're talking about studying these algebraic groupoids and their representations, and you want to do some sort of Tanaka reconstruction theorem for these. Is that at all and then you immediately afterwards said the word topos, which sort of preempted my question. So I was a good setup. There's this theorem, I think due to Joyal and Tierney, which is in the Galois theory of growth, extension of the Galois theory of Grothendieck, that says that every, and I'll lampshade that in quotes just in case, topos is, if you view topos as sheaves on a space, this tells you that every topos is a localic groupoid, right?
Yeah, and then in general, the equivalence of topos is equivalent to some very reasonal kind of
equivalence between
very reasonable kind of as far as I know, pretty reasonable kind of Morita equivalence between these localic groupoids. I mean, almost by definition, you could almost
exactly
the Morita equivalences between the localic groupoids as being topos equivalences.
So do you have a dream then of wanting to say that every, again, lampshading slightly, category that looks kind of like a category of representations should be representations now not over a localic groupoid, but over an algebraic groupoid?
It's something like it's something very much like that, but it's not. But we're not expecting to get equivalences of two categories in this way, unless we add in a lot more fine print. I mean, but we get certain kinds of adjoint two functors between two categories here, and then kind of look at the sort of fixed points of these near equivalences, and you invent very special nice. So you have a difference between these affine algebraic groupoids versus these nice two rigs, but you have adjoint two functors going in both directions, and you have dreams or possibly actual realities, I forget which, of nice characterizations of things that live comfortably in the overlap.
Yeah, I guess I was just asking if the desire to look at algebraic groupoids was at all inspired by the success of localic groupoids in, I guess you would say, the doctrine of topoi or something like that.
Yeah, it's hard to say which direction the influence went. I think for me, I probably didn't really learn about the localic groupoids thing until, but for other people it could have. I don't know exactly. I don't know exactly which. I have a feeling that for me, the flow of ideas was probably in a different direction than the way it was for people who may have thought about it earlier. I'm not quite sure.
For sure, yeah.
But yeah, so one of the reasons I'm in a hurry now is because I stole my friend's computer to do this. I wasn't expecting him to be home today, but I didn't realize it was Martin Luther King Day. And so he's home from work, and I'm annoying him by not letting him use his computer.
Well, I will always have to.
John always has in a quick hurry to leave.
I have many things to do. So anyway, let's.
So I just wanted to emphasize that I'm serious. This time I'm serious. Next time we meet, I'm going to really talk about what I was planning to talk about today.
Okay, good. That sounds good, because I don't know what we'll talk about. So
okay. Anything else we should do before we quit?
No, this conversation's going to end itself.
Okay.
All right.
Okay.
Take care all.
Okay, thanks a lot. I'll see you. Bye.
Bye all.